Hello everyone and welcome to yet another recreational programming session. So in the Porth, the concatenative stack-based programming language that we are developing, recently we introduced a new construction, so-called let bindings, that allow you to take n elements on the stack and assign name to them and use them directly. So let's take a look at some of the examples in here. I need to find the source code of my language on my machine. So let's create a file foo Porth. Let's include the standard library, very important. And let's create the entry point, and there you go. So you can push a couple of elements on the stack, like 10, 20, and 30, and then you can say, all right, let's actually assign these elements on the stack to certain values, like A, B, C. There we go. And then you can work with these things directly. You can, for instance, print A, then you can print C, and for instance, you can ignore B, right? So essentially that will mean that you can only print, that will only print 10 and 30. So, and let's actually try to compile that. Porth compile foo .porth. Maybe we can also run that, and it should print 10 and 30. This construction makes a lot of patterns quite convenient, and I do not regret implementing this thing. However, there is a drawback to this construction. It removes the elements to bind them to certain names, and this is not something that you always want to do. There is like situations quite often actually that you don't want to remove the elements from the stack. You just want to pick into them. Essentially, right, so here maybe I don't want to remove A, B, and C from the stack. I just want to print A and C, and I want to leave them on the data stack for further processing somewhere here. So somewhere here, I'm going to continue processing them. For example, maybe here I will decide to, I don't know, like swap them around or something like that. It doesn't really matter, but usually you just want to pick into the stack. And this situation quite often happens in the loops, right? So in a while loop, you have two sections, while do section, right, which computes the condition, the terminating condition for the loop, and do end section, which is basically the body of the loop. And quite often in a while do, where you compute the condition, like termination condition, you only want to pick into the elements, right? So you only want to pick into them. Let A, B, C, right, to compute the condition, right? So for instance, I want to check that maybe A is not going to be, greater than 10, right? And that's the terminating condition. And then since it removes the elements from the stack, you will have to put them back again, A, B, C, right? And then here you will be processing A, B, C yet again. So it doesn't really matter how we're going to be processing them, but maybe we can just you can try to make some sort of like a Fibonacci-like sequence where the next three elements are going to be B, C, right, so B, C, and then this one is going to be the sum of A, B, and C. Who knows? I don't know, something like that. So, and that's how you compute this entire thing. So, and this situation happens quite often to the point that I'm thinking that we need another construction, which is something like pick, right, which binds the name but does not remove them from the stack. And we already talked about it for like a couple of streams already, and it's obvious that we need to have this construction. And on this specific session, I decided let's just go ahead and implement it. Luckily, we already have all of the necessary machinery to implement that construction, so that should be relatively easy. It's just a matter of adding a new keyword and maybe adding a new construction, instruction, excuse me, a new instruction that basically, binds the name but does not remove them from the stack, and we should be good to go. Let's go ahead and do that, I suppose. So if I try to compile this entire example, I don't think it's going to work. So let me just try to do that. Yeah, it will say unknown word pick. And let's just keep this as an example and keep modifying the compiler until this example compiles, right? So the first thing we probably need to do is to add a new keyword. So let's go into the list of the keywords that we have in here. Keyword. So we have let. Let's introduce keyword pick, right? So this is another keyword. After doing so, the compilation of the compiler is not going to succeed because the amount of keywords has changed, and we have a couple of asserts all around the code that check for the specific amount of keywords. And this is the way the source code sort of reminds you all of the places you have to make modification in to make the keyword happen, so to speak. So let's go ahead and try to recompile the compiler and see how exactly that works. As you can see, the assertion has failed. So I need to add another branch for the conversion between the string representation of the keyword and the internal representation of the keyword. So let's go ahead and do that. So here we'll need to put pick and translate it to pick. And after that, I also need to increment the amount of keywords. So we already have 21 keyword so far, which is a lot of keyword to be fair, but yeah. I don't know, I'll think how to improve that. So right now I don't really care about the syntax, right? So I only trying to develop semantical features. And then once I feel like semantics is more or less stable and more or less what I want, I'll try to think about how to make the language less syntactically noisy. It's already not that syntactically noisy, but still, it would be nice to reduce the amount of keywords, but not right now. Okay, so the opposite conversion we'll have to do like that. So this is pick. So this is 20 and it becomes 21. All right, another one. This is evaluation at compile time. So I don't think we're going to support this thing at compile time. So I'm going to just like increment it and move on. There we go. So assertion in compile. All right. So this is the compilation, right? And keyword let. There we go. So I'm gonna add basically stub in here, keyword pick, and I'm gonna just throw an exception here. Not really exception, but just fail, saying that compiling keyword pick is not implemented yet. Right, I'm going to exit with non-zero exit code, and probably have to also increment this thing. And I think that's it. So yeah, the compiler compiles now, but it cannot compile the example with the pick keyword. Right, so I'm going to try to just run it. Compile, run foo. Right, and it should fail saying that compilation of pick is not implemented yet. So it should fail precisely in here. Okay, that's pretty cool. Now, what are we doing here? So we have a separate keyword for bind. What I'm thinking, we have actually two ways of implementing this entire thing. We can implement it in terms of bind and essentially push everything back. Or maybe, yeah, we can implement only pick that pushes everything to the return stack. And then for the let, we can basically drop the rest of these things, but I don't think it's going to be a good idea. So what I want to do, I want to introduce a separate instruction in the intermediate representation for pick, which acts almost like bind, but it's going to be for picking. Yeah. So let's go ahead and do that. Let me find it, op bind, and in here I'm going to just do pick. And the opposite of the pick is also going to be unbind, I think. Right, so pick is like bind, but it doesn't remove things from the stack. So exact amount of instructions are going to change in the future. Actually, like this applies to everything in this language, right? So I keep repeating that the entire way the language operates, like the semantic, the syntax, the specific implementation, all of that is not stable. It is not set in stone. It is like this right now, and in the future it may change. I'm implementing it the way because I want to just move quickly to the state that I want to see the language in, right? So everything may change. So the specific set of instructions may change. The syntax may change. Everything may change. All right. So all right. So here we'll have to introduce another thing in here. So this one is going to be pick. And we have a 24 instructions now. Okay. Okay, op bind. And I wonder if I can already implement op bind, op pick generation. Because here, as you can see, we're kind of like popping the elements, right? We're kind of like popping them. just to get them? Maybe not. Yeah. So instead of popping them, I'll have to actually copy them from the offset, so to speak. Yeah, we'll see how it goes. So I'm gonna just like put a to do in here, and then in the future it will be more clear how exactly I want to do that. Okay, so this one is gonna be to do. Generating assembly from the peak op peak instruction is not implemented. I cannot see what's going on in there. Is not implemented yet. There we go. Next one. Let's increment this thing. Okay. So, and this is the compilation. Oh, I see what's going on. So I didn't think this particular thing introduces any additional name resolution. So I'm gonna just increment like 24. All right. And this is type checking. Okay, so that's cool. OP bind, and we have a type check bind, which means we'll also have to introduce something like OP type check peak, right? Because bind removes stuff from the type stack, and we won't have to remove it from the type stack. So it's kind of a separate situation in here. All right, OP type pointer int OP peak, and in here what I'll have to do, probably have to also increment this thing and continue, and then just say to do type checking over the peak OP peak, checking of OP peak is not implemented yet. There we go. Cool. And I forgot to increment this thing yet again, so all right, everything seems to be compiling. Compiling keyword peak is not implemented yet. Okay, so now the reason why I introduced that is because I wanted to implement that by basically pushing that thing. So I'm taking the address, the current address, and I'm pushing that address onto the control flow stack. And then I'm adding OP, I suppose, OP peak. Right, and here I'm reusing a function called parse bind list, and I think I can reuse the same parser for peak, right, because it's not that much different at all. Yeah, so I can literally reuse this entire thing. I don't think it does anything special. I don't think peak needs anything special, so yeah, that should be fine. So let's continue and see what's going on in here. Okay, so as you can see now we fail at this very interesting thing and can only close this thing, found peak instead. So we don't know how to enclose peak blocks, right? So we only know how to enclose let blocks, but not how to enclose peak blocks. So let me actually find the place of this thing. By the way, peak should be actually highlighted by Emacs. Let me quickly fix that. So I'm gonna go into the editor support, Porth mode, and let me find the keywords. So here's let, and I'm gonna basically add peak, and I'm going to copy paste this. Should probably add that to all of the editors. So for Vim it should be relatively easy. Where is the let? Here we're gonna have peak, and we also recently got Sublime support. Thank you to Kolumbetka, and I don't even know how to add a new keyword in here, so I'm gonna just try to find let, and so there is a match keyword let. Okay, which is rather interesting. So you have to define this thing. I presume I never actually wrote a syntax file for Sublime, so I have no idea what I'm doing. So, and this is how you do that for the let. And that's a lot of stuff for just matching a single keyword, don't you think? I think it kind of is. So, and wow, very interesting. So I suppose I'm not going to touch Sublime editor yet, but maybe later we'll see. So I would prefer a text editor where it's just as easy as adding a keyword to some sort of a list and be done with it, but Sublime is obviously not one of them. Anyway, so let me go to Emacs local and copy paste the Porth mode. Right, so this is the fresh mode, and I'm going to restart Emacs. I wonder if I have TeamUX. For some reason I don't have a TeamUX. Porth, and let's start Emacs. Okay. So I'm gonna open the example in here, and finally we have the peak. The peak block. What's cool about this thing is that I don't really care about B and C, right? So I can do something like that and don't even worry about them being removed because I don't have to push them back. That is actually pretty cool. I never thought about it. Yeah. So you can just like access any element like in the stack like this by a name and then just like do something with it. That's pretty cool. Really like that. Anyway, let's continue. So I'm gonna do Porth compile porth.porth and then compile foo.porth. Okay. Cool. So I need to find the place where this stuff has happened. Porth.porth. So this is where it happened, and yeah. So op bind. I wonder if I can just use enclose let in here. Is there something special about enclose let that cannot be reused by peak itself? That's a very good question. So op type. I know that enclose let probably checks that whatever we have on the stack is let, but maybe not. So it does op unbind and bind table pop. I didn't think it does anything special, actually. I didn't think it does. Right, so I might as well actually just like literally reuse the whole thing. Right, so type pointer plus 64 op peak. Right, and in here I'm just reuse the entire stuff. And in here I should probably update the error message or peak blocks. Right, so now we have all of that. So a lot of this stuff can be reused. Type checking of peak is not implemented yet. Would you look at that? That's very interesting. We're already at type checking. So the type checking is different, that's for sure. The type checking is different. So I'm going to copy paste this thing, and instead of bind, we're going to say actually type check peak. Right, so let me remove this stuff. And it's not going to compile because we don't have a type check peak, obviously. Right, so let's find type check bind. And can I just like copy paste some of this stuff? There's not that much in here, right? So there's not that much. So here we have a checking data that we have enough elements to bind and stuff like that. So there is the token, there is the context, and how many things you want to bind. And this is an old code. It doesn't use let bindings, so maybe we'll re-implement that code with the let bindings. Type check peak, and here we accept how many things we want to bind. Then the pointer to the token. Right, so I don't remember what's the token, to be fair. I suppose the token is needed for the error message. So I think it's the token of let, right? I'm going to presume that's the token of let. And here we have a context, which is the type checking context. And it simply contains this the stack for like the data stack, the return stack, type stack. Right. So instead of doing these things, I think I'm going to just use let bindings. Let, so we have a bind count, token, and context, and I don't have to create this stuff anymore, which is rather cool. So here we're just doing the check, right? So here I'm just doing the check, and let me see, right? So here I take the context. Since context is not by a pointer, I don't have to do that anymore. I'm accessing its stack, and in a stack I'm accessing its size. So here we have a bind count, and here I'm just checking these two things, and I'm not sure if it's a good idea to do it like that. I might as well do something like this. Just have a let binding. So might as well, by the way, only do something like this. So here is this stuff. So stack size, right? So here is the stack size, and if the stack size is less than the bind count, right? If the stack size is less than the byte count, we'll have to say that data stack does not have enough elements to, in this case, pick, or maybe bind, because bind is more of like a general term. Expected bind count amount of elements, but got stack size amount of elements. It's kind of cool that let bindings makes it easier to implement let bindings, right? So yet another feature that literally implements itself, am I right? So, and in here, since nothing is on the stack, I don't even have to drop anything. I can just do it like that. And that's pretty useful, right? So then I can close this entire stuff. All right, so here's the bind count token. Then in the context, I extract the size, and this is the like let stack size. And I just compare things in here, and that is it. Okay, cool. And then here I'm organizing the loop, and I'm basically popping the elements out of the stack. Which is not particularly great. So I'm basically pushing the top of the data stack into the return, right, and popping the elements out of the stack. But since I don't have to pop them, I can't use the pop operation anymore. So it's out of the, kind of out of the equation. So I'll have to do something slightly different. All right, so I have to push bind count on top of the stack. So this is what we have on the stack. Excuse me. Then I need to basically keep track of the current pointer of the data stack. So I need to take the context, type context stack, right, and I need to get the top of the of that stack. So it's going to be top pointer plus, and I need to read it as a pointer. So this is the top of that stack. And also I need to have an access to the return stack, and I'm not sure if I want to put it on the stack right now. So maybe I'm going to just access it directly from here. But anyway, so I'm going to do while, and this is where pick would be incredibly useful. I could pick into the current bind count and make sure that it's like less, you know, less than 0, actually greater than 0, I'm sorry. But in here, I could just replace that with over, right? I can just check that over that is greater than 0, and I'm going to continue doing this kind of stuff. So, and then let bind count, and this is the top of the data stack, right? So, and in here, what I need to do, I need to grab the return stack. So this is my top, then I need to take the return stack, and then just push it in here, right? So here is the top, here is the return stack, and I push that into the return stack without really removing anything. And then I have to decrement the bind count and get the next frame after the top. So I'll have to do bind count 1 plus, and for the top I'll have to do type stack previous pointer plus read that. There we go. That's how we're going to be doing all of that. All right. So, and after that, do we have to do anything else? So after that, we just like quit. So I have to do drop. There we go. So that should be it, I think. I don't think so. Right. So I wonder if it's going to compile or not. Check pick. Okay, let's try to compile that. Okay, so this thing did not end well because I'm supposed to put do in here. Thank you so much. Unknown type stack, it's actually type frame. Excuse me. It's a type frame. Okay, so the child was terminated by signal 11. All right, so did we just compilation took, okay. So I compiled the compiler. So I got the fourth, then I started compiling foo and stuff like that, and then during the type checking, apparently, I think this happened during the type checking, we've got a seg fault. We straight up got a seg fault, which is rather interesting. So why did we get a seg fault? And by the way, excuse me, I should probably use the Bootstrap compiler as the first layer of the compilation, right? Because it's quite easy to get the compiler into the busted state like that. Busted. All right, so that's very interesting. So where exactly we get that? So if I do something like 69 exit, right, that will confirm that we crashed in the type checking. So during the type checking somewhere there, we actually segfaulted, right? So that makes sense. I wonder where though. So let me see. Is that somewhere here? Okay, so that means it's somewhere in the loop. And I think I fucked up the order of the arguments for this thing. Type stack push frame. So you're supposed to use this. Oh yeah, I see. Because I copy pasted it. Context is not a pointer. All right. So that makes sense. Thank you so much. All right, that's cool. And it still exists abnormally because we have 69. So let's remove 69 and let's go. Still terminated by 11. Okay, so it was obviously not enough. So bind count. So this is a bind count. Context, I take the stack, I take the top of the stack, and that's the top. I do over, and I keep doing that while it's... Oh, I see. I mean, okay. One more time. Sure. Okay, so we have unhandled data on the stack. Ooh, this is actually correct. It is in fact correct. We do have unhandled data on the stack because we didn't drop anything, so that's already something. Right, so the type checking so far is working as expected. Okay, and generating assembly from the pick instruction is not implemented yet. Would you look at that? That's pretty cool. I wonder, like, can I just, like, if I remove this thing, is it going to, like, work properly? So argument do is expected but got integer, right? So and an integer was from here. Okay, so which is understandable, right? So it's just like, yeah, because it only picked into them and then it removed them from the, yeah, that makes a lot of sense. So let me, I think it is like at least the type checking working more or less correctly. So now we just need to implement the assembly generation. Oh boy, let me think how we're going to implement the assembly generation. So here what we're doing is essentially allocating enough memory on the return stack. Right, so we're just doing that, and maybe that's something that we want to do as well, right? So as the first thing in pick, just do that. And then we are starting to push elements into the return stack in here, right? So we pop RBX, right? We pop RBX from the data stack, and then we're moving it into this thing. Right, we're moving it into this thing. I suppose instead of popping it, we'll have to... Oh boy, we'll have to do something about that. We'll have to kind of inverse the index so we compute the proper offset, if that makes any sense. But yeah, okay. So for now, I can also take a look at the foo assembly, a foo asm, and I think foo assembly contains two. Yeah, it contains the standard library. So let's actually remove the standard library from here, and I don't think I'm using standard library anywhere in here. So one thing I probably want to do in here is just like print a, right? So, and luckily print is not part of the standard library, even though print is kind of obsolete, right? It's built-in intrinsic, actually. It's a built-in intrinsic. You can even see its source code in here, right? It's not really source code, assembly, right? And that assembly was generated by a C compiler from a C code. that we wrote at the beginning of the development. So it was like a really quick hack to get something printing on the screen for the language at the early stage of the development. It's not really needed anymore because I can quite easily re-implement this thing in Porth itself. But to do that, I'll have to include the standard library, and standard library includes a lot of garbage, and all of that garbage is going to be actually generated in here, so which makes it difficult to like read the generated assembly, right? So print intrinsic, even though it's kind of like not needed anymore, it is still very useful because like I can use it without the standard library, and it's super easy to read the generated code. Though in the future, maybe this problem can be mitigated by implementing like a dead code elimination, right? So essentially, if you don't use some of the functions from the standard library, just don't include them in the final assembly. But of course, you need to implement that. You need to spend time. And right now I have other priorities, of course. So for now, this print instruction is actually kind of intrinsic. This print intrinsic is actually kind of useful. So anyway, yeah, let me restart this entire thing. And I'm gonna take a look at the full ASM. And the full ASM, and I'm gonna revert everything just in case. And this is where we sort of stop the generation, right? So here is the peak, and we allocated enough memory for 3 elements in there. For 3 elements in there, cool. So, and I'm gonna be starting this thing. So I'm taking the amount of the elements, right? So it's within the operand, right? It is within the operand. And in here I do the dupe, and then I drop the entire thing. So, but instead of pop, what I have to do, I think I have to do the following thing. I have to move into RBX. Right, I need to move into RBX from RSP. But in rex, I'm actually doing plus, right? And in RSP, I also probably have to do plus, right? But I have to add slightly different offsets, right? If I just add this offset, it's not gonna work, I think. I don't think so. We can try to just generate whatever we have right now, just to see what's gonna happen. So let me do that, and something like that, and also let's realign out of the, there we go. So we are just taking element from the data stack, and we're moving that element into the return stack, right? So I don't think x86-64 allows you to move things from one region of memory, like from one region of memory to another region of memory. You have to do that through the register, right? So that's why first we're saving that into the register, and then from the register into a different place in the memory. Okay, so if I take a look at the assembly now, let me revert the entire thing, and there we go. So, so, and this is, okay, of course I forgot the new line. Of course I forgot the new line. I wonder if I can do outer revert on this thing, outer revert mode, and then I can do something like that. Just a second. So I can go here and recompile, and it should just magically update itself. Perfect. So that's what we have in here. So this is the place we're moving this entire thing to, right? But we actually have to move that thing from 0, right? So that means I'll have to get the opposite sort of index of this entire thing, right? So because I'm moving the top of the stack into the like bottom of the return segment. So this has to be more of a like 0. This thing can stay 8, and this thing will have to become 16. So you see, they're kind of moving in opposite directions. Right, so this one goes up, this one goes down, and I just need to organize that in a loop somehow. I need to organize that in a loop somehow. So this is essentially n, right? This is essentially n, and maybe because of that, so I'm doing -1 in here. Okay, so I can put 0 in here, and this is going to be the index. And because of that, I can do is over, while this thing is less than that one. So in here I can have I and n, right? So I can have I and n, and then I can just increment this by 1 and keep the n. Okay, cool. So this one is not needed anymore. Okay, so for RSP, what we have to literally use just I multiplied by 8, right? So it's just I multiplied by 8 because it's a 0 as we saw in the original assembly, right? So it's a 0. But for the rex, it has to be the opposite one. So that means we'll have to kind of take n, subtract I, but it's not going to be the opposite, right? So if you have the indices 1, 2, 3, indices 1 to 3, that means you have 3 elements. So that means if you do 3 minus 1, it's going to be actually 1, but in here you mean 0. So that means you have to do minus 1, additional minus 1, to take that into account. And then you also need to multiply by 8. There we go. So n minus I minus 1 multiplied by 8. So, and then we increment I, and that should be fine. Okay, so and in here we drop 2 things. Here we drop 2 things. Cool. So let's take a look at the assembly. So it doesn't like this thing, which is rather interesting. So, because it's a duplicate. So that means I have to do something like over. Oh yeah, so it's an old code that doesn't use bindings at all. All right, so let's take a look at the generated assembly. Okay. Well, I mean, it generated perfectly, right? So it didn't change at all, which is kind of funny. We can try to just like make it incorrect just to see that it's actually changing, if you know what I mean. Right, so I'm gonna just keep this thing in here. Okay, so as you can see, both of them go in the in increasing order, which is not correct. But then I'm gonna remove this stuff. And now they're going in opposite order. So I think I implemented the code generation. I don't know if it's gonna work correctly, but I think I'm ready to remove this to-do thingy and let the entire thing compile itself properly. So let's go ahead and do that. I wonder if I did not forget anything super important. So far everything compiled, right? So far everything compiled. If I take a look at assembly, so as you can see, it continued doing its thing. Yeah, and then we're essentially done. Okay, let's give it a try. Let me try to literally run the program with the peak. So here we have a program, right? So it uses peak to know when to stop, and then it should print something. So let's actually take a look. This thing has to be less than 10, so it's not going to print anything already. So we have to be super careful. Though we can actually check that it doesn't print anything. I think it's a good idea. All right, so I'm going to try to run the entire thing. And please don't print anything. So it didn't print anything. We can run this thing directly, and as you can see, it doesn't print anything, right? Because the condition here is kind of strange, right? So the a equal to 10, and we only continue when it's less than 10. So let's actually do something like maybe 1000, because I would expect this number to grow relatively quickly. And yeah, we'll see how it goes. It will also jump relatively quickly. So it's actually kind of strange. Maybe we could do something like the next one could be A and B plus, and the next one is B and C plus. Right, something like that. And I don't even know. Well, let's keep it at the original one. Doesn't really matter. We're just testing things. Okay, so we're gonna do 1000, and let me try to run the entire thing. Okay, and it didn't print anything because I didn't really run it, because I didn't provide -r flag. But now it is printing something. Look at that. So 10, 20, 30, and then 60, which is the sum of all of these previous things. And then 110, and I suppose that is more or less correct. So we can try to increase the entire thing by 10,000 and just see how quickly it will grow, right? Okay, so that's how quickly it grows. It actually grows really quickly. The Fibonacci number sequence already grows really quickly, but here we have like 3 numbers in here. Yeah, I guess we just implemented the peak instruction. That's pretty cool. So let me see if the compiler can recompile itself. Because right now I'm actually doing compilation in 2 stages. I'm using previous version of the compiler that doesn't have peak. I'm compiling the new version of the compiler that uses peak, and with that new version of the compiler, I'm compiling the example. So as you can see, the compiler has an ability to actually run whatever program it's compiling. So I'm saying, okay, use the previous version of the compiler, compile Porth and run it, and then I pass the another -r and compile this thing. So that's why there's 2 stages in here. And if I accidentally bust this entire compiler, it's not going to cause any problems because I'm compiling with the previous version anyway. Right, so that's a very convenient setup, and it's pretty safe setup, right? So that's why it takes some time, right? So first I'm compiling the compiler, and then with the new compiler I'm compiling the next program, right? And that's why it outputs a lot of things, because that's a lot of things that needs to be done. All right, so but now I can actually get rid of the bootstrap compiler and just like use the compiler itself, as you can see. Right, and let's just see if it's capable of recompiling itself. Okay, it is capable of recompiling itself, and so far I don't see any problems. It produces the same result essentially, right? Produces the same result, which is nice. So maybe we now need to implement some tests for this entire thing. I might actually add the entire stuff, like this entire stuff, into the test folder. So let's actually rename it to peak, and I'm gonna literally just put it in here. So this is peak, and I'm moving it to here. Then I'm gonna say test by update output tests peak.porth, right? Tests peak.porth, and that should create the expected output for that specific program. So this is basically what this program is expected to output, right? And we can confirm that it actually outputs exactly that. So I probably have to move to here. There we go. So the tests passes. All right. So probably need to add this executable to the ignore list, right? Git ignore peak. All right, so let's create a separate branch. I'm going to call this branch peak. So that's that. And let me see. Okay. Implement peak construction. All right, so I think I remember I actually marked a couple of places in the source code that would be useful with peak. Right, so it's basically off the top of my head, like I found 4 places, and I thought maybe I'm gonna try to use this thing in those places. One is in a snake game, but 3 of them are in the standard library. So as you can see here, right now, you can just like literally go ahead and replace this with peak. Right, so and let's find another peak, and this is literally another one that they're just straight up peak, and another peak, also another peak in here. And as you can see, usually the pattern is in the while do. You usually want to do peak inside of the while do, which is rather interesting. So it actually says something about the whole sort of like looping process. I don't know what yet though. Okay, so let me actually try to recompile the whole compiler, right? So the compiler itself uses the standard library, so now the compiler will be kind of implemented using the peak keyword, which is kind of dangerous, but maybe I'm gonna actually, after the session, reorganize the commits, so we're gonna have this thing in a separate commit, but right now I just want to see if it actually works and doesn't break the whole compiler. Right, because here we're using peak in a very like critical functions like parsing integers or comparing strings and stuff like that, and they're using throughout the whole compiler. So if something goes wrong in here, the compiler is going to break instantly, hopefully, right? So because sometimes maybe you can have like very subtle bugs when the things are not really breaked instantly, they're silently just ignored at some particular point. But anyway, so let's recompile the compiler, right? So let's not run it. And of course I need to do that from here. All right. So, and the compiler is capable of compiling itself. That's actually pretty cool. That is actually pretty cool. And we're literally using the pick construction. So yeah, now you don't have to push everything back. If you just want to pick into something on the stack, right, you don't have to like bind everything and then push everything back. You can literally just like look into that and then just forget about it. So yeah, that's, I guess, it for today. It took 45 minutes to implement this feature, and it was relatively easy because we already had all of the necessary code for this feature to work. So we basically reused like 99% of the lead binding code. The only thing we didn't do is just like, remove the elements from the data stack. So yeah, that's it for today. Thanks everyone for watching, and I see you on the next recreational programming session. Love you. Mwah.